Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Professor Morris. Thank you for meeting me during office hours. I wanted to clarify some principles of quantum computing for my project.
Good afternoon, Mark. Sure. What specific principles are you focusing on for your project?
Mainly superposition and entanglement and how they help with information processing. I understand definitions, but I struggle to see how they become computational resources.
That is a common question. Let us start with superposition. A qubit can be in a combination of basis states 0 and 1, with complex amplitudes alpha and beta. That allows a single qubit to carry more structure than a classical bit.
When you say more structure, do you mean it stores more information at once? Like both 0 and 1 simultaneously?
Not exactly storing extra classical information. Superposition gives amplitudes for multiple outcomes. Measurement still yields a single classical result, but before measurement the state evolves coherently. This coherence allows interference between amplitudes.
So interference is the key to getting useful answers from a superposition.
Yes. Creating a superposition of many computational basis states is often the first step, but you need controlled unitary operations to make amplitudes interfere, so the correct answers have large probability after measurement.
Could you give a concrete example of that process in an algorithmic context?
Take Grover search as an example. You start by applying a Hadamard gate to each of n qubits to create an equal superposition of all 2 to the n basis states. Then, oracle and diffusion operations amplify the amplitude of the marked state through constructive interference.
I see. So if I just had superposition without interference, I would not gain a search advantage.
Exactly. That is why we often say quantum parallelism is only useful when combined with interference and a clever algorithm to extract the desired information.
What about entanglement? How does that differ from superposition in terms of information processing power?
Entanglement is a correlation stronger than any classical correlation. When qubits are entangled, the joint state cannot be written as a product of individual states. This non-separability enables protocols like teleportation and superdense coding, and supports multi-qubit interference patterns used in algorithms.
Teleportation is the protocol that moves a quantum state using entanglement and classical bits, right?
Yes. You share an entangled pair. Through a joint measurement and 2 classical bits sent to the receiver, the original unknown state is reconstructed at the remote qubit. That shows entanglement can be a resource for transmitting quantum information without physically moving the particle.
Is entanglement necessary for speedups in algorithms like Shor or Grover?
The role of entanglement is subtle. Many quantum algorithms do generate entanglement across qubits. For Shor factoring, entanglement appears during modular exponentiation and Fourier transform steps. Entanglement often underpins the complex interference patterns that produce a computational advantage.
Could a quantum computer that never generates entanglement still outperform classical computers?
Most known exponential speedups require entanglement at some stage. There are limited cases of algorithms with only limited entanglement or other quantum correlations. But scalable, general advantages usually involve entanglement.
You mentioned Hadamard and the Fourier transform. Are those examples of quantum gates that create superposition and entanglement?
Yes. A single qubit Hadamard gate transforms a basis state into an equal superposition. A two-qubit controlled NOT gate, the CNOT, can entangle a control and target qubit when the control is in superposition. Combined gate sequences create complex entangled states and perform computations.
How should I visualize a qubit state during these operations? The block sphere helps with single qubits, but what about many qubits?
The block sphere is great for single qubit intuition. For multiple qubits, the state space grows exponentially and visualization becomes difficult. We often rely on mathematical representations and reduced density matrices. Still, the block sphere shows how unitary operations rotate states and how measurement projects them.
What about noise and decoherence? You mentioned coherence earlier as important for interference. How big an obstacle is decoherence for these principles?
Decoherence is a major obstacle. It destroys phase relationships between amplitudes, and therefore ruins interference and entanglement. Practical quantum information processing needs long coherence times, or active error correction, to protect superposition and entanglement during computations.
Could you name some physical platforms and how they address decoherence?
Superconducting qubits have relatively fast gate times and use cryogenic circuits. They focus on improving materials and circuit design to reduce noise. Trapped ion qubits have long coherence times and high-fidelity gates, but slower operations. There are also proposals for topological qubits that aim to be intrinsically protected from some errors.
You mentioned error correction. How does that relate to superposition and entanglement?
Quantum error correction encodes logical qubits into entangled states of many physical qubits. The encoding and syndrome measurements use entanglement and controlled operations to detect and correct errors without measuring the logical information directly. So entanglement is crucial to error correction schemes.
I am curious about a simple calculation. If I apply Hadamard to each of 3 qubits starting in 0, what do I get?
Applying Hadamard to each of 3 qubits creates an equal superposition of all 8 basis states from 000 to 111. Each basis state has the same amplitude magnitude, so you have parallel amplitudes across the entire computational space.
So that is the basis for quantum parallelism. But you still need the rest of the circuit to make the amplitudes useful.
Correct. Also keep in mind measurement will collapse the superposition. The art of algorithm design is to engineer the interference so the measurement yields a high probability for the correct solution.
Are there simple experiments or demonstrations I could include in my project that show these principles?
Yes. A basic demonstration is generating a Bell pair using Hadamard and CNOT, and then measuring correlations. Another is showing interference by preparing a superposition and applying phase shifts before recombining. If you have access to cloud quantum hardware, you can run these circuits on superconducting or trapped ion processors.
That sounds doable. For my presentation, I will explain superposition, interference, entanglement, and include a Bell pair demonstration plus the Hadamard parallelism example.
That is a good plan. Emphasize the distinction between having amplitudes for many states and the need for interference and entanglement to process information. Also mention decoherence and error correction as practical constraints.
Thank you. One last question. Is there a concise way to summarize why quantum principles matter for computing?
A concise summary is that superposition provides a high-dimensional state space, and entanglement creates strong correlations across that space. Together, with coherent unitary evolution and controlled measurements, they enable new modes of information processing that can outperform classical methods for specific tasks.
Perfect. I will use that summary. I appreciate your time and the practical examples.
You are welcome. Email me your draft and I can give feedback on the technical accuracy and clarity for your audience.
Listen again to part of the conversation. Then answer the question.
If you apply a Hadamard gate to each of n qubits, you create a superposition of all 2 to the n basis states, and that is the starting point for quantum parallelism.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.